Hello and welcome everyone to lecture 15 of EC 3030. Today we will continue our discussion on PN junctions. So today's lecture will focus on deriving a quantitative relationship for the relationship between current and voltage in a PN junction. So in the previous lectures we have looked into the band diagram, how it changes as you apply forward bias voltage or reverse bias voltage, and how the depletion width changes. This lecture will focus on the current voltage characteristics. Alright, so today's lecture we will be following section 3.2 and section 6.1.2. The analysis that we'll be presenting today in the lecture will be much more simplified than what is discussed in the textbook. So but anyway, to better your understanding of the topics, you should go through the reading list. All right, so we'll first start with the concept of diffusion, because this concept is required for understanding the current voltage characteristics of a PN junction. So diffusion means that carriers or particles will flow from a region of higher concentration to a lower concentration, and this is all happens because of the thermal motion of the particles. So at any temperature T, the particles has an energy of kT multiplied with the number of degrees of freedom. So at temperature T, the absolute temperature T, an electron or hole will have a thermal energy of 3 kT, and as a result they just go through a random motion like this. And due to this random motion, if there is in the one region there is a higher concentration of electrons or holes, they will on average flow towards the region of lower concentration, and that's the concept of diffusion. And this is actually what we have seen also in PN junctions. So when we make a contact with the P and N type region, then the holes from the P type region moves to the N type region, and the electrons from the N type region moves to the P type region and creates this depletion region. So that is one example of diffusion. Now today the diffusion that we'll be talking about, we will use to understand how the current actually flows when you apply a forward bias voltage or a reverse bias voltage. All right, so so the diffusion current essentially is the current that flows due to the diffusion of the particles. For example, in this case here, the case shown here, for example, you have a semiconductor material and you're injecting carriers from the left side, and as a result what is happening is that you have a higher concentration of particles at this edge, and then it decreases as you go to the right. Why it decreases we will explain in the next slide, but say it decreases like this, and the current that you will flow will be proportional to the gradient of the carriers. So say we are talking about P type carriers, and for the sake of simplicity let's just consider the magnitude here. So this current density due to the gradient in hole will be proportional to the gradient of holes. So say over a distance of x, the carrier density, the hole density decreases by an amount of delta p. So the diffusion current due to the holes will be proportional to delta p divided by delta x, and this proportionality constant is usually written as like this: Jp equals q dp delta p over delta x, and for the sake of simplicity we'll just consider the magnitude here. All right, so and this proportionality constant is called diffusion constant. And similarly for electrons, Jn you can write equals q dn multiplied with delta n over delta x, the change in n over a distance of x. So this is a simplified version. The proper version is the differential, but for the sake of simplicity we just write is a ratio of two differences. Okay, so here, so we have two quantities, the hole diffusion constant dp and the electron diffusion constant dn. So this is called diffusion current, and this diffusion constant is actually related very closely to the mobility. And this is actually an equation derived by Einstein, and it says that the diffusion constant is proportional to the mobility, and the constant of proportionality is kT over q. And similarly, so for holes, dp equals to mu p over kt, and for electrons dn equals mu n over kt, mu n multiplied with kt over q. All right, so this is an important equation, so we'll not derive it, but this is something we'll just take it for granted. Okay, so now we talked about diffusion. Now the thing is that once we inject some carriers, dissimilar carriers, we also say that the density of that injected carriers decreases as you go away from the source of the position of the injection. And the idea is this. So say for example you have a p-type semiconductor here, so the positive ones basically represent the holes, and say you have introduced these electrons here. Now what will happen is that due to the thermal motion they will move around, they will diffuse through the semiconductor, and after they go a certain amount of distance they will combine with some holes, and as they combine with the holes they recombine and basically they disappear. So again you had injected some electrons into the sea of holes, they diffuse, and after some traversing some distance they recombine and disappear, and this recombination essentially creates a situation where the location of injection has the highest density of the injected carriers, and as you go away from the location of injection the density of those injected carriers decreases, and after some distance there is no you won't see any of those carriers. So there are some these are the related quantities that we define. So here Ln is the average distance that an electron traverses before recombination. So we had these electrons here and they moved this much of distance Ln, and then they recombine with this hole. So this is Ln, and tau n is effective the average time before the electron recombines. So this electron traveled Ln amount of distance for an average amount of tau n, and then it recombined. So these are the two important quantities that we define to describe the diffusion and reaction recombination process. And another important quantity relationship is this, that the diffusion length is equal to the diffusion constant multiplied with the diffusion time. Similarly, if you have an n-type semiconductor and introduce some holes, Lp is the diffusion length for those holes, the average distance the holes traverse, a hole traverses before recombination, and tau p is the diffusion time, which is the average time a hole traverses before recombination. And again for the hole the similar relationship holds, Lp equals dp multiplied with tau p. All right, so again we did not derive these equations, we just take them for granted. So this will be required for quantitative calculations. Okay, so now let's get back to p-n junctions, and as we have shown in equilibrium in a p-n junction, the electrons and holes from the p side goes towards the n side, and the electrons from the n side goes towards the p side, and they recombine and create the depletion region, and the depletion width is set by the built-in voltage, and built-in voltage is set by the doping densities. Okay, now we apply a forward bias voltage greater than 0 So the p-type semiconductor has a positive voltage with respect to that of the n-type semiconductor, and what will happen is that the depletion width will decrease. And the second thing that will happen, which we have not yet discussed, is that this p-type p side will inject holes to the n side. So this p side will inject holes to the n side, and the n side will inject electrons to the p side. So these are the injected carriers that we have seen. So this is what we discuss in this lecture. All right, so the hole should be coming from this side. Okay. All right, so now what we have plotted here is the carrier densities in the p side and the n side. So as we have said, the p side will inject holes into the n side. So this is what we are plotting here is Pn, the hole density in the n-type semiconductor. Note that this is n-type semiconductor, so holes are minority carriers. And this is Pn0, and Pn0 means the carrier density of the n-type semiconductor region, and this is basically equal to Ni square over Nd. Okay. So now what we have said is that this p-type semiconductor injects electron holes into the n-type semiconductor, and as a result the concentration at the edge of the depletion of the holes is actually larger than the equilibrium hole density, and so this is what we called Pn at x equal to Wn, and this is actually equal to Pn0 e power qv over kt. Now why is there a factor called qv over e power qv over kt? The reason is that once you apply a voltage, forward bias voltage, the barrier for holes to go from p to n actually decreases by qv amount, and whenever there is a barrier lowering, the carrier densities increase, the carrier injected carriers increase by a factor, exponential factor over qv over kt. Now the argument that we are giving here is very hand waving, but nonetheless this relationship can be formally derived, and this relationship is actually called the law of junctions. So now this is actually derived in the textbook for this, but for the sake of the class we will just again take it for granted. Okay, so now this is what we have. So now what we can write is, what is the value of the diffusion current due to the injected holes in the n side? So we will say Jp, the current due to the holes injected into the n side, and this will be equal to q d of p, the diffusion coefficient for the holes in the n side, multiplied by delta p. Now okay, so what is delta p? Delta p is simply Pn x equals Wn minus Pn. So now what we have said is that the average distance this access holes traverses is equal to L of P in the n side. So what we will say is that x equals to Lp in the n side over the distance. So this is Lp over n, and if we simply do the calculation, this will come out to be like this: q dp Lp over n multiplied with Pn0 to the power Qv over Kt minus 1. And which direction does this current flow? This current flows in this direction. Jpn flows in this direction, the positive x. Alright, so now similarly for the n side, we are plotting here Np. N means electron concentration on the p side, and the equilibrium concentration of electrons is Np0, and this is equal to Ni square over Na. And again by the law of junction, so this is the depletion width and this is negative Wp, and this was x equal to, this was x, so this is again, so this direction is x minus p, and this distance after which the excess carriers goes down to the equilibrium value is the diffusion length for electrons in the p side. And by the law of junction, this value of carriers at the edge of the depletion of the p side is N p at x equals minus Wp equals Np0 e power Qv over Kt. Okay, so the diffusion current density for the electrons in the p side is equal to Q, diffusion coefficient for electrons in the p side, multiplied with N, the p side at x equal to minus Wp minus N of p, x equal to minus Wp minus lnp. So here this x should have been x, this is equal to Lp plus Wn. Okay, so over lnp, and if we plug in this here, what we will get is Q dnp over lnp multiplied with np0 e power Qv over Kt minus 1. Alright, and this current, so electrons are decreasing in this side, so this differential is in this direction, but if electron flows this in this direction, the current will flow in the opposite. So the electron flow will be in this side, but if current flows in this direction, if the electrons flow in this direction, then the current will flow in the opposite direction. So the diffusion current due to the electron injection into the p side from the n side will flow in the positive direction. So both Jpn and Jnp will be in the same direction. So the total current density J equals Jpn, the current due to the whole injection from the p side to the n side, and Jnp, the current due to the electron induction into the p side from the n side, and it will be equal to Q multiplied with dpn over dlpn multiplied with pn0 plus dnp over lnp multiplied with np0 multiplied with e power Qv over Kt minus 1, and this quantity we called J0. To summarize, in the forward bias, the depletion width changes, so the depletion width becomes smaller And the second thing is, second phenomena is that minority carrier injection. So holes are injected into the N side from the P side, and at the edge of the depletion, the hole density in the N side is equal to the equilibrium hole density multiplied with e power qv over kt, and this Pn0 is the equilibrium hole density in the N side and is equal to Ni square over Nd, and the electron injected into the P side from N side equals to the equilibrium electron density in the P side, which equal to Ni square over Na multiplied with e power qv by kt. And so this is the equation that we just derived. Here note that this dPn is the diffusion coefficient of the holes in the N side. Lpn is the diffusion length of holes in the N side, and similarly dNp is the diffusion coefficient of electrons in the P side, and Lnp is the diffusion length of the electrons in the P side. All right. So if we so this is the current density, and the current I is simply J multiplied with A being the area of cross section of the PN junction. And if we plot J as a function of V, this is how it will look like. In the forward bias, it will have an exponential dependence, and the reverse bias, it will be constant. So also what we can do is that we can write it as J naught e power qv over kt minus 1. Now one thing to remember is that if in the forward bias, if the voltage is larger than 3 kt over q, then this e power qv over kt becomes much larger than 1, and as a result J will be equal to simply an exponential function of qv over kt. On the other hand, if v is smaller than 3 kt over q, this e power qv over kt will be much smaller than 1. As a result, J will just simply be equal to minus J naught. So here this value is minus J naught, and in the forward bias it will just be an exponential function. Now although we have derived this equation for forward bias, this is equally valid in the reverse biased, which we'll get more idea as we look into the calculated carrier density profiles in the forward bias and the reverse bias in the next slides. So first look at the evolution of the carrier density and the excess carrier density in the forward bias, and also the evolution of band diagram in the forward bias, which you already seen in the previous lecture. Alright, so this is the equilibrium condition where the voltage is 0, and as like the previous lecture, the doping densities are the P side has a higher doping density than the N side, and this is the same doping density as we have seen in the previous lecture. So previous lecture we have we plotted the depletion charge, free space charge densities, the electric field, the electrostatic potential, and the band diagram. Here we are just plotting the band diagram and the mobile carrier density beyond the depletion regions. So outside the depletion regions, now at Vd equals to 0, there is no, the carrier densities are exactly same everywhere because there is no injection of holes from the P side to the N side and no injection of electrons from the N side to the P side. So the carrier concentration remains the same everywhere. So it's just the base is used as the equilibrium carrier density. Now if we apply a voltage, then the carrier density increases at this edge of the depletion region, but it's very small, we cannot see it. But now as we increase, we see that the electron density has increased, hole density at the interface has increased, and it goes down as we go away from the depletion region due to the recombination. And similarly, the excess carrier density for the electrons injected into the P side from the N side has increased it is the maximum at the edge of the depletion region, and as you go away from the depletion region into the P side, this decreases due to the recombination. And as you increase the voltage, just these carrier densities keep on increasing. All right, so again, let's see how the carrier concentration changes as you apply a small signal voltage on a DC voltage of 0.25 volts. Now what you can see is that the depletion region changes a little bit, and the carrier concentrations also changes as you increase or decrease the volt forward bias voltage. And also you can see that the depletion region is also changing its position here. All right. Okay, so now let's look at the same thing in the reverse bias, the evolution of carrier density and the band diagram in the reverse bias region. Okay, so here again, the zero voltage case. So what we have done here is, in this case, what we have plotted here is the carrier densities, equilibrium carrier densities. So this is basically a Pn0, which is Ni square over Nd, and this is Np0 equal to Ni square over Na. So in the previous couple of slides, these values were both 0, because in those cases we subtracted Np0 from Np and Pn0 from Pn. Now we are just plotting Np, and on the left panel and the right side we are plotting Pn. Alright, so at equilibrium, zero voltage, we have there is no carrier injection, so the carrier densities for minority carriers are flat throughout outside the depletion region. Now if we apply a negative voltage to the P side, basically reverse bias, then we can see that the carrier density at this edge of the depletion region, minority carrier density actually decreases. Now in the forward bias it was increasing in the depletion region at the edge of the depletion. In the reverse bias, the carrier density, the minority carrier density acts actually decreasing. And as we increase the reverse bias voltage, this carrier density keep on going down, and when this carrier density is larger than 3 kT, negative the reverse bias voltage is larger than 3 kT over Q, then what happens is that this access carrier density actually the carrier density, minority carrier density at the edge of the depletion region actually goes to 0 here. And now if we keep on increasing the value of reverse bias voltage, this region, the slope of this region no longer changes, and because it's already pinned to 0, and this is why the reverse bias current actually becomes constant, because the reverse bias current or the diffusion current is proportional to this slope, and when the reverse bias voltage is larger than 3 kT over Q, then this slope essentially becomes constant, and as a result the current does not decrease anymore. Only thing is that the depletion width now keeps on increasing as we increase the voltage. All right, so again the same thing. Now we are plotting how the depletion width and the carrier concentration changes as we apply an AC voltage on top of a DC voltage of negative minus 0.15. So basically this PN junction diode is reverse biased, and on top of the DC voltage we are applying a small AC voltage, and what you can see is that the depletion width changes and how the carrier densities, minority carrier density changes at the beyond the edge of the depletion region. All right.